2, 3. All right, so in this video, we're going to take a look at logic circuits. But let's first do a brief introduction to basic digital electronics. We're going to start from here. This is taken from a book called Practical Electronics for Inventors, another book that I recommend. So it says, until now, we have mainly covered the analog realm of electronics, circuits that accept and respond to voltages that vary continuously over a given range. Such analog circuits include rectifiers, filters, amplifiers, RC timers, oscillators, simple transistor switches, and so on. Although each of these analog circuits is fundamentally important in its own rights, these circuits lack an important feature. They cannot store or process bits of information needed to make complex logical decisions. To incorporate logical decision-making process into a circuit, you need to use digital electronics. All right, so let's continue from here. In digital electronics, there are only two voltage states present at any given point within a circuit. These voltage states are either high or low. The voltage being high or low at a particular location within a circuit can signify a number of things. For example, it might represent the on or off state of a switch or a saturated transistor. One bit of a number, whether an event has occurred or whether some action should be taken. All right, so let's look at something here. This is an analog signal. As you can see, the analog signal is all over the place, has a lot of variation within the voltage in a signal. And this here is a sample of a digital signal. So as you can see, it has only two states. It can either be a 0 volt or a 5 volts. All right, so in digital electronics, this is 5 volts. This state right here, 5 volts, is called a logical 1 or a high. And this state right here is called a logical 0 or a low. And so digital electronics is represented with a binary numeric system. Binary numeric system only has two digits, ones and 0. All right. I'm going to start from here. It says logic gates are logic gates are circuits designed to produce the basic logic functions and or etc. These circuits are designed to be interconnected into larger, more complex logic circuit arrangements. Since these circuits form the basic building blocks of all digital systems, we have summarized the action of each of the gates in the next section. For each gate, we have included the British standard symbol together with the American standard symbol. We have also included the truth table and Boolean expression using plus to denote or, the dot to denote and, multiplication to denote and, a minus to denote, and this symbol here to denote not. Note that while inverters and buffers each have only one input, exclusive OR gates have two inputs, and the other basic gates and OR and NAND are commonly available with up to 8 inputs. So the first gate here is the buffer. It says buffer do not affect the logical state of a digital signal, i.e. a logical 1 input results in a logical 1 output, whereas a logical 0 input results in a logical 0 output. So let's take a look at a buffer. This here is a symbol of a buffer. As you can see, it has one input, one output. This is the American symbol. This is the British symbol. But mostly you're gonna find this symbol in books. And this here is the truth table. So as you can see, X is the input and Y is the output. So when there is a zero, a logical zero in the input, you have logical zero in the output. And when you have logical one, you have logical one in the output. Next, next is the inverter. It says inverters are used to complement the logical state, i.e., logic 1 input in a logical 0 output, and vice versa. So the inverter, if you take a look at the symbol of the inverter, it's basically a buffer, the same thing as a buffer, but it has this circle in the output, and what this means is that it's negating the input. So if the input is a 1, a logic 1, it's going to negate that input. So it's going to have a 0 on the output. This is a truth table for an inverter, and this is the Boolean expression for an inverter. Y is the output. Y is equals to not X. All right, so Y is equals to the input negated. Whenever you see this line on top of a letter, that means that it is negated. So next, AND gates. It says AND gates will only produce a logical 1 output when all inputs are simultaneously a logic 1. And this is the Boolean expression of an AND operation. Y, the output, is equals to the multiplication of its inputs. This here is the AND symbol, and this is the truth table for an AND operation. So as you can see, Y being the output, an AND has two inputs, A and B. Y being the output is only at a logical high, or a 1, when both its inputs are 1. All right? So basically, it's the multiplication of binary numbers. You're only going to have a 1 when both inputs are high. Next is the OR gate. The OR gate, this is the Boolean expression of an OR gate. The output is equals to the addition of its inputs, and this is the symbol. This is the symbol right here. So in Boolean, when you add in two binary numbers, of course, 0 plus 0 is equals 0. 1, any combination of 1 and 0 is equals 1. And 1 plus 1 is also 1, because in binary, you cannot have a 2 or a 3. It's always represented with 1 and 0. It's only state 0, low or high, represented by 0 or 1. So as you can see, when both inputs are 1, you're going to have a 1 on the output. Next is a NAND gate. This is the Boolean operation for a NAND gate. So the output is equals to the negation of the multiplication of its inputs. And notice the circle here at the output. It multiplied its input and then negates the output. So it's a NAND gate, but the output it's the output is negated. So if the AND gate, the multiplication of two binary zeros in the AND multiplication is 0, because it's here negated, it makes it a 1. So if you look at the table here, 0 times 0 is 0, with a negated output makes it a 1. So 1 times 1 negated is equal 0. So that's for the NAND. The NOR, which is the symbol here, is an OR gate but negated. You're going to have to learn all these symbols and truth table and the Boolean expression. And then we have the exclusive OR. The exclusive OR, it's an OR gate, as you can see. But always look at the Boolean expression. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 in the OR gate should be 1, but here in the exclusive OR is 0. This is a symbol of exclusive OR. It has this thing in the input. And so that is for this video. Thanks for watching.